This tutorial will show some of the powerful tools SAP 2000 offers for the sophisticated modeling and analysis of concrete box girder bridges. The bridge we will model will be 200 feet long with 2 spans, with a deck 36 feet wide and a depth that varies as a parabola. It will support 2 lanes of traffic, each 14 feet wide, and it will be pre-stressed in the girders of the concrete box section. First, we make sure that the units are set to kip feet. The majority of commands that we will use to create the model can be found under the Bridge menu item, including a Bridge Wizard. A quick check of the Bridge Wizard shows that it describes the basic procedure and each of the steps. As you step through each operation, a description is provided, and you may choose to define or modify your data if appropriate. However, for this example, we will create our bridge model directly from the commands on the Bridge menu. We start the process by defining a layout line, which provides the primary control geometry for our bridge. We will specify a starting station at 0 feet and an ending station at 220 feet. The layout line is slightly longer than the actual bridge to accommodate skews. By using the Quick Start option, we can quickly define the shape of the horizontal layout. For our model, we will use straight line geometry. With the layout line geometry defined, the next step is to create the bridge deck section, which is again found under the Bridge menu. Here, the program offers numerous parametrically driven templates, and we will choose a concrete box girder with vertical sides. Verify that the total width is set to 36 feet and that the initial depth is set to 5 feet. The Bridge Objects command is where we control the placement of items in the bridge model. First, we'll move the abutment 10 feet in from the end of the layout line. Next, we will add a bent at midspan. Lastly, we will move the right abutment 10 feet in. Next, we will skew the abutments 15 degrees. We will skew the bent in a similar fashion. All the items defined up to now have been part of a bridge object definition. In order to convert these definitions into a SAP object-based model, we need to link the model. The SAP model may be created as a spline model with frame objects, or with area or solid objects. In our case, we will be using the area objects. SAP 2000 has taken our bridge object definitions and created a structural model with area objects and supports at the left, the midspan, and the right. Next, we will modify the abutments. We will allow the bridge to translate normal to the abutment, and will support the bridge at each girder. We will also provide a vertical diaphragm or end cap. Next, we will modify the bridge bents. There will be 3 columns for this bent. Clicking on the Modify Column Data button, we can locate the columns at 2.5, 15, and 27.5 feet along the bent. We can also vary the height of each column. In this next step, we will define the parabolic variations of the deck depth. This is done through the parametric variations command. We will have two different variations, one for the left span and a second for the right span. The depths will vary by a total of 5 feet and will be constant for 10 feet on each side of the bent. Now that the variations have been defined, we assign them to the spans using the bridge objects command. Clicking the Modify Span Definitions button, we can change the section from constant to varying based on the previously defined parametric variations. In order to see the depth variation, we will switch to an elevation view. Next, we will define a pre-stressed load case. Now, under the Bridge Objects command, we will define the pre-stressed tendons. Clicking the Modify Pre-stress button allows us to add a new tendon. We will add tendons that are post-tensioned and span the entire length of the bridge. The tendons will have an area of 10 inches square with a force of 1,500 kips and will be modeled as loads. For the vertical layout, we click on the Quick Start button and choose a parabolic shape. We will accept the default layout, and we can now see the tendon position over the entire length of the bridge. Next, we copy the tendon just defined to all of the girders. If we click on the Show All Tendons button, we see in the section view how the tendons vary along the span. If we remove the area objects from our view, we can see the location of each of the pre-stressing tendons. To define our loading, we start by defining two lanes using the lane command. Because our model has been generated from a layout line, we will use the same layout line for the lane definition. Our first lane will be offset -9 feet, and all lanes will be 14 feet wide. Note that we will define the ends of the lanes beyond the ends of the bridge. We will change the display color so that it is easier to see. The center line of the first lane is shown relative to the layout line. Our second lane will be offset 9 feet on the other side of the layout line. Again, we will change the display color so that it is easier to see. If we go to the display command, we can view the lane widths rather than just the center lines. Next, we define the vehicles that will run on the lanes using the vehicles command. In this case, we will use a standard vehicle, a HS20-44. The next step is to assign the previously defined vehicle to a vehicle class. Vehicle classes allow you to group more than one vehicle together for the bridge response. Now that we have defined the lanes and vehicles, we need to set up the moving load analysis case. Our new analysis case will be a moving load with our one vehicle class applied to all lanes with a factor of 1. Prior to running the analysis, we will select our bridge response quantities. In this case, we will simply shut off the section cuts option. We are now ready to run the analysis. Upon completion of the analysis, the deformed shape for the dead load case is displayed. Next, we will display the deformed shapes for the other analysis cases. Note that for the pre-stress case, the displacement is in the up direction, as expected. We can also plot influence surfaces for the moving loads. Here we will plot the axial force response in a column. Next, we will plot the bridge forces along the length of the entire bridge. Now we will unlock the model to allow us to add a moving load case for trucks. Under the load case command, we will add a case called trucks with a type of moving load. Clicking on the Modify Moving Load button allows us to define our loading patterns. We will load the bridge with 3 trucks, the first being in lane 1 moving at a speed of 40 feet per second. The next truck will be in lane 2, starting at the opposite end of the bridge, moving in the opposite direction at 40 feet per second. The third truck will again be in lane 1, but will start 1.5 seconds behind the first truck. We will set the total loading duration to 7.5 seconds. And we will discretize at 0.3 seconds. We are now ready to once again run the analysis. However, this time we are interested in the results for only the truck's case, so we will set all the other analysis cases to do not run. As done for the previous analysis cases, we can view the bridge forces for the truck's case. We can display the forces for either the entire bridge or for individual girders. We can also plot the stresses in the shell elements. Here we will display the F11 component at step 9, which is close to midway in the analysis. Lastly, we will switch to an OpenGL view to plot the trucks moving over the bridge. Make sure that the truck's analysis case is selected and increase the magnification factor so that the deformations will be obvious. We also want to use the Show Vehicles option. We can see the movie being created at each step. Once the movie has been created, the viewer will play it in a repeated loop. This concludes this tutorial.